not that easy to tell which one of these might be a more accurate intrinsic description of the shapes of elliptical galaxies. This prolate cigar shaped looking thing, probably not too likely, although there might be some ellipticals like that. A better candidate may be the oblate ellipsoid, except we found the fact that if that is true, it's not flattened in this direction because of rapid rotation of elliptical galaxies. So that was a hit against that. And so we have an increasing amount of evidence implicated triaxial configuration that has three different axes, one really long one intermediate one, and then one shorter one is probably a better description. For example, there's the fact that if you had just an oblate ellipsoid, you would never see so-called isophotal twists, where the inner parts of the galaxy seem to be at a different position angle from the outer parts. It just wouldn't be if it had the rotational symmetry of an oblate spheroid. Another, you get these special kinds of orbits, so-called box orbits of stars, in a triaxial potential, but not in an oblate spheroid potential. The stars actually do these X box. If you have a lot of stars doing those fascinating X orbits, then you can explain this previously not explained fact. Look at this galaxy in the bottom here. There's a real classic elliptical galaxy, and you can see that it has this excess of stars on these box orbits. It requires a somewhat triaxial gravitational potential to explain this. It just shows you some of the box orbits that you get, which explains why some elliptical galaxies are boxy. Now, this difference, some galaxies are not, that some galaxies have disky isophotes and some elliptical galaxies have boxy isophotes, is more than just completely random curiosity. It must be something fairly basic. There's a fundamental difference between the elliptical galaxies that look disky and the more classical elliptical galaxies that look boxy. The powerful radio sources are always in the boxy elliptical galaxies. Boxy means that this fourth coefficient of a Fourier description of the brightness as a function of theta, of angle, is negative. Anyway, so the boxy ellipticals are over here, and they're all the powerful radio sources. A triaxiality is common in elliptical galaxies, but not by very much. Do we have any theoretical predictions about how a system of stars, mutual gravitation of billions of stars moving in the gravitational potential caused by the other stars? This has a very close mathematical equivalence with the problem of a collisionless gas. To make the analogy very accurate, there's a velocity dispersion. That's the average speed, basically, the RMS speed of the stars. That is directly analogous to the average speed or RMS speed of molecules in a gas, which is direct. If you square that, that's the kinetic energy of the particles. That's usually directly equated to what? KT, or 3/2 KT if you're talking about all three dimensions of the motion of a particle. So yes, you could actually quite well describe the random motions of stars, their kinetic energy, as a temperature of a gas. Stars are so tiny, small, compared to the separations between them. It's nothing like any gas. Even a perfect vacuum that you could make on Earth still has a lot higher density of molecules in it than the incredibly low density of these teensy little stars. Stars will never actually collide with each other. They're too little and too far apart. So how could they actually influence individual other stars gravitational? You could have the accumulated effects of distant passages, which would give a slight deflection, like a fraction of a degree, to what the star was going before. Then the star passes over here, it pulls the star a little bit over this way. Then millions of years later, there's a star over here, gives the sun a little bit of kick in its direction that way. Then another millions of years, it's that way. This is little kicks, accumulation of hundreds or thousands of these kicks. It's exactly like a random walk. It's like flipping a coin. It might pull you this way, it might pull you that way. But if you have thousands of these distant interactions with other stars, it will eventually start to move you away from the original direction you were going. So after a really long time, which is called the two-body relaxation time scale, the star, like the sun, will basically have forgotten which way it was originally originally going, and it'll be going off on some new random direction. So I used to have like whole slides. I worked this out, actually. You can work out the time scale. When you plug in the numbers for the density of stars, how fast they're going in the Milky Way, this takes quadrillions of years. So this two-body relaxation process has never happened. Let's go with something that actually is important and does play a role because it's much, much faster in changing the orbits, changing the directions, changing the speeds of stars dramatically in a short time. But you need to have a system which is seriously out of equilibrium. Have a galaxy that has large lumps or large clumps or pieces of galaxies or other galaxies that are falling in. There's not a smooth potential of gravity, and the gravitational potential is changing as one star tries to complete its orbit. By the time a star has gone through around the system once in some orbit, the gravitational potential that's pulling on and accelerating has changed during that time. Suppose a bunch of stars have like almost identical initial properties. Stars, like the inner one, will have a somewhat shorter orbit period, and the little outer one will take a little bit longer to orbit. So by the time they've just gone around a few orbits, even if they started together, after they've gone around once or twice, they're spread out in their orbit. They're no longer at the same phase, called phase wrapping. And so after just a few orbits of these stars, which might be just a few 100 million years, the stars are all around. They started out all together in space, but now they're all wrapped around a fairly similar orbit at different locations. These are actual numerical simulations. Little overdense regions collapse into clumps. You have a very clumpy profile. Then these clumps dance around with each other and change the gravitational potential dramatically while stars are trying to move through this stuff. And what you see is quite rapidly it begins to settle down into some kind of equilibrium. This is in just a few orbits. As time going across like this and continuing, it settles down to a pretty smooth looking distribution. It's very well described by a de Vauqueler's R to the 1/4 brightness law. This is a more sophisticated simulation n-body code with more particles in it. It's about 6 galaxies falling into each other here. For example, as to how the galaxies, when they come close, interact with each other. They tear out these tidal tails, woo, from each galaxy. You can see they had a close encounter then. Then they fly apart, but then they're going to fall back together again and stick, because these individual encounters between two lumps are extremely sticky gravitationally. This is partly because of dark matter. These guys are coming in, and now they're really stuck. They're going to merge. And then these others are further out, but they're going to merge also. So we started, some galaxies are rotating, some galaxies are in disks. Doesn't really matter what the starting conditions were. Boom, they're all going to end up in a few orbits pretty much looking the same no matter what you start them out with, because of violent relaxation. It's getting more simple here, isn't it? It's looking kind of more spherical, by the way. The random velocities are just taking over. There's no disk now. Any disks that were there are destroyed by this process. It's going to take a while for the disk to form. This thing here looks amazingly like an actual elliptical galaxy. What are some of the effects of this violent relaxation process? In a fairly short time, you are going to establish something which obeys the Virial Theorem. The stars are going to establish themselves with an average velocity dispersion, an average kinetic energy per star, just dictated by the gravitational potential. They're going to have the same temperature. But here's one difference. Not the same as if there were actual collisions where individual stars would transfer their kinetic energy to another individual star. That's not how it happens. The gravitational potential energy that's changing gives accelerations to the stars. What's the difference? When the gravitational potential energy is changing rapidly over time, it accelerates all masses the same. In this room, all of the particles here have the same average kinetic energy. The heavy molecules are moving slower than the light ones. That is not what happens in violent relaxation. all of the objects end up not with the same kinetic energy, but the same kinetic energy per unit mass. They end up with the same average velocity. Process goes pretty far, violent relaxation, but it doesn't go all the way. You can still have these remaining anisotropies. The velocity dispersion is different in different directions. It's very weird to think of. So there actually are different temperatures depending on which axis you're measuring the stellar velocities. There's the equilibrium, sharing out the velocities of the stars. So they're all going to have the same velocity dispersion, the same temperature, elegant mathematical treatment of particles all having an identical temperature, isothermal, one temperature, one velocity dispersion. An isothermal sphere, that's a bunch of particles with a constant temperature, a constant velocity dispersion, is a surprisingly good description of actual elliptical galaxies, and maybe also a good description of the dark matter halos. I'm just going to give you a result here. This naturally tends to give you a density distribution, if it's spherical, which falls as 1 over the square of the distance from the center of the system. A 1 over r squared density law. You can do the integral in a spherical system, right? The integral of all the density here would be the integral of r goes from 0 up to infinity of r squared dr times rho of r. Whoops. Rho of r has a 1 over r squared in it, so when I integrate over these shells, these volume elements of 4 pi r squared dr, the integrand, the little r squared on the bottom here, cancels the volume element r squared on top. It increases linearly with radius as you integrate more and more an isothermal sphere. What does that tell you about the orbital velocities? Flat rotation curve. Two problems with it. So what would the total mass of such a galaxy be? Infinite. There must be a cutoff here where at some point the mass stops increasing, stops falling as 1 over r squared and falls off much more rapidly, a tidal cutoff. Another thing, this has a singularity at r equals 0. This was a nice description, which has quite a lot of reality in it, but it must be wrong at very large r, where real galaxies just end, get cut off. And it also cannot really be a good description in the center of the galaxy either at r equals 0. This is how it's actually fixed in the middle. You modify the solution to have a core where the density eventually in the center inside the core levels off to a constant value. And the typical ratio between the inner core of an isothermal sphere and the outermost limits of the galaxy where it's tidally truncated, by the gravity of other galaxies, is typically a factor of 100 in radius. Well, some galaxies do have cores in their centers, which is somewhat like what an isothermal sphere was supposed to be, but some galaxies do not have cores, constant density regions in the center. Some of them, the density just keeps on going up, not as 1 over r squared, but like as 1 over r in the middle. I don't think that was really very well predicted by anybody. Oops, but there's quite a remarkable correlation. Remember the boxy elliptical galaxies that don't rotate very much? Those are the ones that do have a proper core, a region of constant density in the middle. The rapidly rotating ellipticals that have disky isophotal contours have these central cusps. Different galaxies interact with each other. Stars are ridiculously widely separated compared to their sizes. Stars never encounter each other. Galaxies are huge, big fluffy things, and even today, after the universe has been expanding for 13 billion years, they're still not that far apart from each other. Here's a typical example. This is the M81, M82, I think M83 group of galaxies. This is a nearby group of galaxies, and you say, hey, the separations between these galaxies are not that many galaxy diameters. Galaxies must occasionally have gravitational interactions with other nearby galaxies. The interactions might be quite dramatic. Of course, we cannot sit here and wait millions of years for these galaxies to actually come together. If you have a radio telescope, it's really dramatic. They don't seem to be doing anything to each other. But look at what happened to the outer envelopes of the hydrogen gas. The neutral H1 is revealed by a radio map with 21 centimeter. Look, they're tearing streams out of each other on the right here. These galaxies have clearly been altering each other. The first thing that's most likely to happen when you have the passage of one nearby galaxy with another one, as you saw in the simulation, is a stream, a tidal tail will be torn out from the other galaxy. And who knows where it might end up. This gas might end up transferred from one galaxy to another, could even condense and form a new galaxy. And clearly these tidal streams or tidal interactions are going on before our very eyes. Although you don't really notice it very much in the inner parts of the galaxies. The stars, it's not obvious that they've really done much. Sometimes the interactions are closer together and you'll see the stars get these tidal arms and distortions quite unmistakably. I mean, M51 would be an example. Remember the Whirlpool galaxy? Those two galaxies are really in close interaction. This is a less obvious one. Here's a seemingly just by itself elliptical galaxy. What the heck are these sharp shells? A real concentration of stars over here, and there's one over here. They're on opposite sides. This happens when a small galaxy falls into a big galaxy and gets torn apart by the tidal force of the large galaxy. It comes in on an elliptical orbit, and where do stars spend most of their time on a highly eccentric orbit? At maximum distance, apogalacticon. So they move real slow there. So what's happening here is these are alternate apogalacticons of stars, and they pile up there and make these shells. So all of these shells, and you can see a lot of shells around ellipticals, say that ellipticals, some maybe hundreds of millions of years ago, it consumed, it cannibalized a smaller galaxy. And you can see, if you look carefully, you can see these shells as proof, evidence that happened. These are famous objects. Here's a simulation on the left. What happens when you have a big disk of a galaxy and a little object has a penetrating collision? It actually goes through it, a little bit like dropping a pebble in a pond. It sends out a compression wave, and you can get these beautiful ring galaxies. Here's one galaxy here, and it has eaten another galaxy. It looks more like a disk galaxy. And now this galaxy, I think, rotates this way, but this galaxy is in orbit over the pole. Several percent of galaxies today have these weird collision merger morphologies. And you're wondering, what about the Milky Way? I mean, or Andromeda? It doesn't look that weird now, but maybe in its past, it also went through collisions and mergers like this, with smaller galaxies usually. And the answer is, yeah, it probably happens in the histories of most galaxies. It's just a question of how big the merger was. Was it a minor merger, just a dinky little object fell in? There are minor mergers happening today in the Milky Way. Little dwarf galaxies are falling into the Milky Way. The Magellanic Clouds, I guess, will eventually fall in, and so on. But it probably hasn't had a big impact on the Milky Way in billions of years. Look at the rotation velocities. This is a slow rotator here. So on one side, you got your blue shifts. On the other side, you've got your red shifts. It's a slow rotator. What the heck is going on in the center of this galaxy? This is actually not unusual in elliptical galaxies. There's a rapidly rotating core in the center of the galaxy. The core is rotating the other way. This elliptical galaxy that was rotating this way ate another substantial galaxy that was rotating the other way, and you can still see it in there. There's one other example of this, a category of galaxies called CD galaxies, dense-looking core and a very diffuse envelope around it. CD galaxies, it's an elliptical galaxy, but it doesn't really obey an r to the 1/4 law in its outer parts. See, there's an r to 1/4 law. See, I've got r to the 1/4 on this axis. You remember this from Tuesday. There's your brightness profile, surface brightness. It actually has this huge extended halo going way out here of extra light. That's how it's defined as a diffuse galaxy. CD galaxies only found in one place in the entire universe, in the centers of rich clusters of galaxies. These are a product of a rich cluster of galaxies. This is what happens when you put a rich cluster of galaxies together. It's what happens when a lot of galaxies collide. You get this huge halo. This is all eaten, cannibalized galaxies that have just merged together here. So this is kind of proof that some elliptical galaxies, at least, are the product. They were built by, they were produced by merger after merger, eating smaller pieces, eating and eating, maybe dozens, maybe hundreds of little pieces of galaxies forming modern elliptical galaxies. Sometimes you can actually see multiple nuclei of these galaxies. They're still eating them today. The density is highest, so the chances of two galaxies encountering is higher, happens more often than when they're far apart. The most massive galaxy, as we'll see in a minute, is naturally going to sink into the center of gravity. CD galaxies are by far the most massive galaxies in the universe. Here's the process. This process of dynamical friction is another way that the orbits of objects can be altered. This is a little different from violent relaxation. This is what happens. Dynamical friction is the process when you have many small mass objects, black dots. One more massive object, which has a big M here, and it's in red. I might be thinking of a massive galaxy in a cluster. The low mass objects are other galaxies. There's going to be dynamical friction. It operates to slow down the motion of the large mass object. If the big mass object has any motion at all with respect to the stars, then it's going to systematically alter the orbits of the stars as it drifts through. The little object have their orbits as they pass by the big mass object pulled towards the big object. So the ones up here are systematically pulled this way. The ones down here are systematically pulled that way. In other words, the large extra gravity of the large mass forms a wake behind it if it's moving at all. So if it's moving in this direction here, the wake is a region behind it of higher density. It's called gravitational focusing, but you know that. These stars have had their orbits piled up to where there's a higher density of them behind the big mass, because the big mass altered their orbits than the density initially in front. These objects haven't been influenced yet. They haven't had their encounters yet. Whatever direction the big mass is going in, it always finds there's a higher gravity, a higher mass density behind it than there is in front of it. It's a drag. This is a really strong effect if it's a really big mass compared to these little masses. A big mass object will always have its peculiar special velocity taken away. It will lose whatever orbital velocity has, and in a relatively short time, it will spiral down into the center of mass, like here. Now, it's at the center of mass of the cluster, so it's hardly moving anywhere, so now there's no force on it. It had all of its orbital speed in this cluster sapped away by dynamical friction. Schematic representation of the nearby universe. Okay, so we're already in a overdensity of galaxies, right? It's unusual to have a galaxy as big as Andromeda as near as it is to us. Plus we got about, I don't know, a dozen or 20 other galaxies in the local group. It's probably gravitationally bound, the Magellanic Clouds, and a few other dinky little galaxies, the companions to Andromeda. So we're probably all going to merge eventually. So obviously galaxies aren't just uniformly distributed, but it's much more dramatic than that. If you look at the bright galaxies, most of the bright galaxies that you can see in the sky, if we're talking like 13th, 14th magnitude galaxies, they're mostly in the northern hemisphere, like 2/3 to 3/4 of them, because the Virgo cluster is in the direction of the Virgo constellation. It's just named after that constellation of stars. Is in the northern hemisphere, and that is the largest concentration of nearby, that means bright, galaxies in our local part of the universe. So it's grossly inhomogeneous. There's no equivalent concentration in the south direction. The Virgo cluster of galaxies is a typical unimpressive cluster of galaxies. The Palomar Sky Survey, probably the most important sky survey that was ever done in history. The soon as people started developing these photographic plates, you pull them out of the fixer, you look at them and you say, oh, look at that. there's a bunch of galaxies together. The great astronomer George A. Bell produced what is still useful today as the first catalog of galaxy clusters simply by visually inspecting all of these photographic plates that he and others had taken. I inherited his actual office. This is a deep photograph. That's a star in the Milky Way. Sometimes it's easier to see these, positive prints instead of negative prints instead of positive prints. So there's a big, bright, ooh, what kind of galaxy do you think that is in the center of the cluster? It's a CD galaxy with this huge halo. There's some kind of S0 galaxies. They sort of look disky. There's a lot of elliptical galaxies in this cluster, and it just sort of extends out. How many galaxies are there in this cluster? For every massive galaxy, there's way more, dozens of low-mass galaxies. A. Bell was practically said, I'll just count the bright galaxies in the cluster, and I'll classify how rich it is. Virgo Cluster is like the most pathetic cluster that A. Bell even bothered to catalog. Richness class 0. What a put down. Finally, he got up to his highest richness class. What is that? Richness class 5 here, where he only found one such cluster in the entire sky as you could survey from Palomar Observatory, and that's the Coma Cluster. In a class by itself, hundreds and hundreds of bright galaxies, thousands and thousands of fainter galaxies in the Coma Cluster. What is the mass of everything in a cluster of galaxies? Hundreds or thousands of visible galaxies, mostly ellipticals and S0 galaxies. Galaxy clusters have a real deficiency of spiral galaxies. You add up the mass of all of those galaxies. We know we've already measured the masses of individual galaxies. Is that the mass of the cluster of galaxies? No way. There's way more dark matter. Dark matter was discovered by studying clusters of galaxies because you have a sample of hundreds of galaxies and you can weigh the whole thing. 3 ways of measuring the total mass, everything. Apply the Virial Theorem to the individual galaxies in the cluster by measuring their velocities. The Virial Theorem tells you that most of the mass in galaxy clusters is not stars. It's not luminous matter, it's dark matter. Right, that's the Virial Theorem estimate, made first by Zwicky, shows the mass to light ratios. This is if you add up the total mass in solar masses in the cluster Coma, and then you add up the total luminosity in solar luminosities, you get an outrageously high ratio. The mass to light ratio is like 500 times what it would be for the sun. Almost all of the mass of the Coma cluster, and these other clusters too, is dark matter. Okay, people didn't take this seriously. So what forced them to take it seriously was when new observations came along. Nobody predicted it. The first telescope that was launched above the Earth's atmosphere that was able to focus somewhat X-rays. Some of the X-rays were coming from famous clusters of galaxies like the Coma cluster. Who predicted that? Nobody predicted that. You generally associate that with very high energy processes. Electrons in a very hot gas produce X-rays. Thermal bremsstrahlung, that's free emission. So if you have a very hot ionized gas, the electrons are moving around at high speeds because it's very hot gas, and every once in a while they'll have an encounter with an ion, breaking radiation. It causes the electron to accelerate. Whoops, accelerating electron, that produces photons. That's how you get electromagnetic radiation. The X-ray telescope had accidentally found out that all clusters of galaxies are filled with hot gas, millions of degrees hot, up to 10 million degrees hot, and it's producing an enormous glow of X-ray emission. 10 million degrees is so hot, how does the gas stay in the cluster? Wouldn't it have escape velocity? What's keeping that gas, that hot gas, from escaping? The dark matter gravity of that cluster is strong enough to keep the gas in equilibrium, hydrostatic equilibrium. And you need a galaxy cluster dominated by dark matter, or else all this X-ray gas would have evaporated. Light blue glow here is what an X-ray imaging telescope sees. And this cluster is filled with gas, a lot of gas, but it's the temperature of the gas being so outrageously high. They didn't need Zwicky. They didn't need to measure the individual orbital velocities of galaxies. They could have simply measured the X-ray temperature of this gas and concluded it's held together in equilibrium, assuming it's not escaping. We always assume hydrostatic equilibrium. It's held together by an enormous gravity of dark matter was found, which also confirmed exactly what Zwicky was saying and exactly what the X-ray astronomers were saying. These clusters, which are ensembles of huge numbers of galaxies, most of the mass here, most of the gravity, more like 95% of the mass is dark matter. How do we really know that the Virial Theorem applies? How do we really know that the hydrostatic equilibrium condition applies? Maybe they're not in equilibrium. I think some people said that to Zwicky. You said, well, temporarily you're measuring some very high velocities, but I'm sure if you wait long enough, all those galaxies will just fly apart. But Zwicky was correct. He said, I don't think so. How lucky would that be? I think that they've been together for a long time and they're staying together. I think it's gravitationally bound.